The front part of this section dealt with the collision model, and the second part of that section dealt with activation energy. Both of these are models that we discussed, and what we want to do now is do a mathematical treatment. Activation energy will be used for our calculation, and think about how would you draw an exo and how would you draw an endothermic reaction. That's what I have on the next page. Here we have our exo. We have our reactants. We have our products. And what we have here is an activation energy, the EA. That is the line that takes you up to the transition state. On the second part of the slide, we have the endo. Here we have the reactants. Here we have the products. And once again, we have an activation energy. My drawings aren't perfect, but the ones in your textbook are, okay? So if we're going to treat reactions, we're going to use the Arrhenius equation. And for most reactions, I have to say most, you see an increase in rate with increasing temperature, and you also see that it is nonlinear. You notice it is not a straight line. This is the Arrhenius equation, where K is the same rate constant we've dealt with in the chapter. A is a constant that we don't talk about too much in 1220. But what we really want to talk about is that activation energy. R comes to us from the gas law. This time we use the energy unit. And T, it is going to be in terms of temperature Kelvin. So it matches the ideal gas law. So now you can really see that K does depend on temperature. The greater the value of EA, the smaller the K. Well, it's a higher hill to climb, and the slower the reaction rate. Why is that? Well, there's fewer collisions that take place with sufficient energy to go over the barrier. So on this slide, I kind of visited again because it is a very important topic. You've seen me say so many times, lower temperature, higher temperature. Here it's beautifully color-coded. So conceptually, you can see that the red area has more molecules with kinetic energy that can undergo reaction. But what about looking at the math of it? All right, so what I did is I chose some exponents for my E. All right, that's kind of how I went about it. I made some numbers and I started with K, and I'm always working with activation energy. So essentially, you can see how the K gets smaller and smaller and smaller. So if we have a larger K and a larger EA, our K is definitely going to decrease. I did these calculations at a constant temperature because I really wanted to show what is the impact of the EA. You may have a conceptual question or, again, working up data. It's important to know this. We can't test you on it, but it's something that we really need to make sure you know. Here is the Arrhenius equation, and if I rearrange it, what I can come up with is a way to look at it where I've taken the curve and turned it into a straight line. The slope of that line is minus EA over R. And all I have here on the right is the data. Someone looked at temperature, someone measured their rate constant. They got this curve, all right? But if we're looking for the EA, what we want to do is we want to use ln K as our Y. We want to use 1 over T as our X, and we're able to make a graph where we can now come up with the slope. Again, can't ask you that on an exam, but there may be a lab this semester where you're actually doing this hand-on. So since you can't do it on an exam, we'll probably give you a different sort of question. This is the Arrhenius equation using 2 points. Notice there are 5 variables, 1, 2, 3, 4, 5. If you were with me in Chemistry 1210, we talked about this format of equation briefly, and now we're introducing it in terms of the EA. So what are the possibilities? Well, you will always get 4 out of the 5, and the 5th is the one you will calculate. Since they're mathematically quite involved, what I did is I worked them out before I made this video. How does the rate constant change with a 10-degree rise in temperature? I would just pick an EA, let's say 50, and I had to then pick a temperature range. That's one example. Example 1 that follows. Example 2 says the rate constant is tripled when the temperature increases by 10 degrees. Find EA. So again, you are given 4 out of the 5 variables in the Arrhenius equation. For this first one, if my EA is about 50 and I have a 10-degree increase in temperature, I just pick these numbers, 27 and 37 degrees. Then what I did is I substituted them into the equation, and I'll be honest, I evaluate everything here on the right side, came up with a numerical answer. What I did then is I said K1 over K2 is e to the minus 0.6466. When I evaluated that, this is my relationship between K1 and K2. So K1 is half of K2, or K2 is twice K1. This is the famous rule of thumb they'll refer to in a textbook. Near room temperature, well, that was like 27 degrees, the rate of the reaction approximately doubles with a 10-degree rise in temperature. But I write, use this in caution because it depends on the EA. A different EA, you're going to get a different answer. What's the next slide? The next one is where the rate constant is tripled. We're doing this as a group because I want to show you how do you carry this out. When someone says rate constant is tripled, I said, hey, K2 is equal to 3 times K1. And what we have is 298 as our T1, 308 as our T2, and we substitute everything into the equation. Sure, there are K's here, but they're going to cancel out. Once again, I'll mathematically evaluate the expressions. And again, it does boil down just to simple algebra. And I come up with an EA of 83,833 joules per mole, which then I turn into kilojoules, but I forgot to put the K there. So if you only have values for K1 and K2, there could be an error in finding EA because K was only measured at 2 temperatures. So what you want to do if you're working is you want to obtain K at many temperatures. That's why we use the graph when we're working in the lab, but if we're on a test, we tend to make it more of a mathematical problem. Finally, sample exercise 1410. You may be expected to rank the rate constants. And you're seeing here, I don't see any rate constants. Well, what you do see are activation energies. If this is my reactant and this is my product, I have an EA forward that is equal to 15 kilojoules per mole. And what about my EA reversed? Oh, I'll make that with like a little squiggle line. My EA reverse, that is going to be equal to a 15 plus 10, or 25 kilojoules per mole. So from these rate constants, 15 for the forward and 25 for the reverse, you can make some predictions about the K. And I will leave that up to you because you've got a textbook, and for me to show you, it doesn't really help you learn it. Got to work through it yourself. So take a look at sample exercise 1410. Assess your EAs, and as you know, as EA increases, the K is going to decrease. But EA can be coming from 2 different places, from the forward or the reverse.